Hi, the asymptotic notations are languages which is containing some simple symbols to allow the algorithm analysis in terms of running time by identifying the algorithm's behavior, and the runtime will increase when the input size is increasing from 1 to n number of input. The asymptotic analysis of an algorithm defining the mathematical bounding or mathematical framing of its runtime performance. To compare the algorithm's functions, we are having different asymptotic notations. The algorithm's functions in the sense, suppose if you are having the any algorithm, that algorithm is having some set of behavior based upon the performance, based upon the operations, primitive operations. For example, sum is sum of n number. We will have the statement sum equal to sum plus I. Here we will have for loop I equal to 1, then I less than or equal to n I plus plus. So here we are having set of statements. Here the statement I equal to 1 will run for one time, and then statement I less than or equal to n run for n times. I plus plus will execute for n times. This assignment will run for n times, and plus will addition operation will perform for n times. So which is having uh, this is 1 n time, I plus plus 1 n time, then assignment operation 1 n time, addition operation for n time. So here 4 n plus 1. So like this for this algorithm we are having the function for n plus 1. So like this each and every algorithm will be assigned with its function based upon the number of primitive operations performed in the algorithm. So based upon this we are having set of notations, big O notation and small O notations. Both are useful to calculate the upper bound of an algorithm. Upper bound in the sense maximum running time, maximum runtime consumed by the given algorithm, right? Then we are having big O and small o notation, which is measuring the minimum time consumed by the algorithm for its execution. Then one more notation, theta notation, which is called tighter bound, which is calculating the average time consumed for the algorithm's execution. So we are having five notations for measuring the performance of algorithm by using set of functions. Here the big one notation having two functions f of n and g of n. That means for given problem statement, for example, if you are writing the algorithm for addition of addition of two numbers. So for addition of two numbers, you assume we are having two different algorithms. That means different number of variables and different number of statements. So if we are first algorithm is having one statement, 5 statements. Then second algorithm is having 7 statements. So here, based upon this, the function will be varying. So assume f of n is calculated from the algorithm 1 with 5 number of lines, and g of n is the function which is calculated from the second algorithm which is having 7 number of lines. So here the f of n is equivalent to big O of g of n. Here n is representing the input size. This statements can be read as f of n is order of g of n, otherwise f of n is big O of g of n. If there are constants c and n0, here c is the constant, then n0 is the input, some input, such that for n greater than n0, so n is the maximum input size, n0 is one of the input size less than n0, c is always greater than 0, n0 also greater than 0. So if it is the case, with these assumptions, f of n, the function of n of the algorithm 1, always less than or equal to c into the g of n, which is related to the second algorithm. So the function of n is always less than or equal to c into g of n. So whenever the function is satisfying this condition, at that context we can use the big O notation to represent the algorithm's behavior. Here the figure represents when we are increasing the input size from n0 to n, how is the behavior of f of n and g of n is varying, right? So here this is the function which is denoting the f of n. So here when we are changing the input size until n0, until the input size n0, the f of n is above the c into g of n. Here the c into g of n is low, less than f of n, until the input size is n0. After that, so here this location f of n is equal to c into g of n. After this location, this c into g of n is always greater than f of n. So the function here f of n less than c into g of n. So here, which is equal to c into g of n, which is less than c into g of n. So when you are increasing n0, then n1, then here n2, here n3. So when you are changing your input size until n, f of n is always less than or equal to c into g of n. So this condition satisfies the condition f of n less than or equal to c into g of n. If it is the case, this functions satisfy the big O notation. Then next, here we have seen we will see one example. This is for the first algorithm f of n calculated, so 10 n square, and g of n, the second algorithm which is having the function n cube. So here the f of n, and for c into g of n, so here c value is 1, c value is 1 because we are having the n cube, coefficient is 1, so c equal to 1. The f of n is 10n square. When we are changing the n value, this is input n, right? So this is the maximum size of n. Here we are having the n0 is this one. This is the n0, not this one. N0, right? So here until n0, you look at this yellow color line is c into g of n. So until n0, the c into g of n is less than the f of n. So until here, this function not satisfying the big O notation. After this, after n0, when you are increasing the input size 11, when f of n is always less than the c into g of n, when you are substituting n equal to 10, f of n is 10 into 10 square equal to 1000. Likewise, when you are substituting the n cube, 10 cube, so which is also 1000. So at the point of n0 equal to 10, both are equal. F of n equal to c into g of n. But when you are substituting the 11, c into g of n will be greater than the f of n, so which is satisfying the big O notation. Here the in big O notation, I have given one of the example. So for some algorithm we are getting the function 7n minus 3. So as per the given conditions, if you are having the function with the lower order term, so when your n is getting large, you can omit the lower order term, so we will get the 7n. Then in the 7n also, in this coefficient, this is 7 times of n, so you can ignore the coefficient of n, so finally you will get big O of n. This is also big O, right? So likewise for the second algorithm, another one algorithm, where we are getting the function 8n square log n 5n square n. Here the lower order terms are n, so we can ignore this. In this two terms, here 8 times of n square log n, here only 5n square, so 5n square is lower order term comparing with 8n square log n, so finally you will get 8n square log n. In this 8n square log n, 8 is the constant which is the coefficient to this term, so you can ignore this. Finally we are getting big O, or big O of order, big O of n square log n. So this is the way to calculate the time complexity by using big O notation. Now the small O notation, second asymptotic notation to calculate the time complexity, assume again two algorithms. The two algorithms are having different function values. The f of n one function, g of n is another function. When f of n is only less than c of n, always less than c into g of n, then we can use the small o notation, right? In the big O notation, f of n is always less than or equal to c into g of n. But here the small o will use only f of n less than c into g of n for all the input size n. Here also we are taking c constant, n0 is the input size which is less than the large input size n. That's what given here. C is always positive number, n0 is also positive number. So here, when you are increasing the n, when you are increasing the n into large size, that means infinity, f of n becomes insignificant relative to g of n when it is approaching the infinity, right? So you look at that, suppose we are having input sizes 1 to infinity. Suppose n equal to 1 lakh, n equal to 1 lakh. So when you are n equal to 1 lakh, here the condition is f of n is always less than the c into g of n. Here we are having one constant value, that is positive number, then n is increasing. So when n is increasing, it will get large because we are having constant and g of n. And also one more condition is the f of n is always less than the c into g of n, so which is always low value than g of n, so which will be insignificant comparing with g of n when n is approaching to the infinity from low number of inputs. So here the g of n is maximum time, okay, upper bound, okay, maximum time which is consuming by the runtime algorithm with comparing with f of n, that is not asymptotically tight, not tight, that means g of n will consume maximum amount of time. That's what the meaning we have to observe in this context. Third one, big omega notation. Here, if you want to say some algorithm is taking or consuming at least 5 minutes, the algorithm is consuming at least 2 minutes, so the minimum time is represented by using the big omega notation. The big omega is the symbol which is used to express lower bounds, that means minimum amount of time consumed by the given algorithm, that is represented by using the big omega symbol. Assume f of n and g of n are two functions of the given algorithm, then f of n is big omega of g of n if there exist positive numbers, that means always c is also greater than 0, n0 also greater than, sorry, n0 is less than n, but n0 is greater than 0, n0 is greater than 0. So based upon that, f of n always greater than or equal to c into g of n. So always f of n value will be highest than c into g of n. So which indicates the big omega notation. That means at least that algorithm will consume some amount of time to run or its execution. So here this figure, you look at that, when until n equal to 0, f of n is less than, f of n is less than, okay, less than the c into g of n. After, at the point of n equal to n0, at the point of n0 both are equal, f of n equal to c into g of n. After this, f of n is greater than c into g of n, okay, f of n value is greater than c into g of n. So after this n0, the f of n greater than or equal to c into g of n, which is satisfying the big omega notation. In this location we can use big omega to represent the time complexity. For example, 3n plus 2. So big omega of 3n plus 2. Here again, as per the time complexity criteria, when n is getting large, lower order term can be ignored and coefficient can be ignored. So finally we will get big omega of n. The next one, small omega notation. So again assume f of n and g of n are two functions which are computed from the two different algorithms for the given problem statement, single problem statement. Here f of n is always greater than c into g of n. In the previous big omega notation, f of n is greater than or equal to c into g of n. But here the small omega notation represents when f of n is just greater than c into g of n. Here also f of n value and c into g of n value always greater than 0, and c is greater than 0, n0 also greater the positive number, both are positive numbers. The n0 value is less than or equal to n value. Here also when f of n is, when n is increasing into large value towards infinity, f of n will be large. Okay, f of n will be large because f of n is always greater than c into g of n, c into g of n. So when your n is increasing into infinity value, step by step our f of n value getting large, the g of n will become low value. So the g of n is the lower bound for f of n. So this function will consume lower time when comparing with f of n. So this is not asymptotically tight. The last one, big theta notation. So the previously we have seen upper bound, that means maximum time consumed by the algorithm, which is represented by big O whenever f of n is less than or equal to c into g of n. Then we have seen small omega notations for algorithm which is consuming minimum time. Here f of n is always greater than or equal to c into g of n, right? If it is the small omega, this is also related to the minimum time computation, but f of n is always greater than c into g of n. Now if you want to calculate the average time, the algorithm is not consuming low time and also maximum time, it is consuming average time. So for this we can go with theta notation here, which is called tighter bound, which is denoted by big theta symbol. F of n equal to theta into g of n. Theta of g of n means always f of n equal to big O of g of n, f of n equal to big omega of g of n. So here the f of n is equivalent to order, satisfying the order of big O of g of n and also big omega of g of n. That means which is satisfying the upper bound and also lower bound. So when it is the case, we will take two constant values c1 comma c2, both are always positive numbers, and n0 also positive numbers. So here the c1 into g of n less than or equal to f of n less than or equal to c2 into g of n, right? We will take two functions, then we will use the two constants c1 and c2. Then whenever you are applying the c1 value and c2 value to the second algorithm's function g of n, this will be here f of n always will be greater than c1 into g of n, less than C2 into G of n. So this portion, okay, this portion is tighter bound, average case, after the input size n0, always f of n is greater than c1 into c1 into g of n, less than c2 into g of n. So this in this context we can go with big theta of g of n. Okay, so this represents average time consumed by the given algorithm. So here g of n is asymptotically tight bound for f of n. So tight bound in the sense average time. Okay, f of n is average time consumption. So from this, what we are observing, f of n is equal to big theta of g of n. That means average time consumption. We can say f of n and g of n are growing at the same speed, same rate when you are increasing the n value from n0 to infinity, which are growing at the same rate, both algorithms. But second observation, f of n is equal to big O of g of n, that is upper bound. F of n not equal to big omega of g of n, which is not lower bound. If in this context we can say f of n, function f of n is asymptotically slowly growing than g of n, because here the condition is for big O, f of n is less than or equal to c into g of n. So f of n is always less than or equal to g of n. So here f of n is slowly growing than g of n. The third observation, f of n is equal to big omega of g of n. That means which is f of n is consuming minimum time. That means it is representing the lower bound, but which is not upper bound. F of n not equal to big O of g of n. In this context, we can say f of n is asymptotically fastly growing than g of n, because f of n is here greater than or equal to c into g of n. So f of n is always large value than c into g of n. So which is fastly growing than c into g of n. See, these are the three observations we should note from the this asymptotic notations. Which notation we will use among these five notations to express the efficiency of algorithms? Which of the three notations should we use? Which of these five notations actually? One is big O, and another one is small o, and big omega, small omega, theta. So which of the which notation mostly will be used among these five notations? As a computer scientist, generally like to express the algorithms by using the big O, because the big O is representing the upper bound, maximum time consumed by the algorithm when you are increasing the input from n0 to infinity, that means or n. So this maximum time includes average time and also some lower bound time. So this upper bound includes average, I mean tighter bound, and also lower bound. So when you are considering upper bound, automatically it includes tighter bound average time, lower bound minimum time. So the scientists always will use big O notation to represent the time complexity. So when you are getting the upper bound, you can try to reduce into the smallest value by altering some number of primitive operations. So the upper bound is the worst case time, worst I mean maximum time, worst, that is called worst. Then if you reduce the run time, then it is called you are improving the algorithm by reducing some number of statements without affecting the result. So you can reduce some time, so that time indicates you are improving your algorithm's performance. Here some functions have been given. Constant time consumption. So constant time, so whenever we are running the statements only once, if you execute some statement only once or only few times, two times, three times or five times, so that statements consume constant amount of time, order of 1. Then when we are increasing the n into large value, so the some algorithms that large problem will be break into smaller problem. Okay, smaller problem, then smaller problem will be executed and find out the result. So for that, when you are breaking the large problem into smaller problems, then the time consumption will be log n, half of the n approximately. Then when you are increasing the value from n0 to n, here the execution time will take also n equivalent to n number of inputs, so at that time algorithm will consume order of n. When n is doubles, the runtime also slightly more than doubles. So here when n is increasing, for some kind of problem that can be break into smaller problems, which can be that smaller problems can be solved independently. So in this context we will get n log n time complexity. For quadratic equations, when n is increasing into doubles, then runtime also increase fourfold. So this kind of algorithm will consume n square time complexity. So example, insertion short. If we are having increasing the n into 3 times or doubles, then it will consume eightfold of time for cubic function. So that is order of n cube. When you are increasing the n into exponential value, then it will perform square of your n. So with this kind of problems use, this kind of complexities are used brute force solution. So for example, here the 2 power n log n and n log n square always very greater than compared for the even less input. Okay, for the less input, the polynomial time consumption will be very less. Here for high input, always the greater than this two complexities n cube and 2 power n, but which is the non polynomial. So with this I conclude the session. Here we have discussed asymptotic notations and how the asymptotic notations are used to calculate the behavior of the given algorithm using functions. That function will contain calculated based on number of primitive operations performed in the given algorithm. Thank you.